As you know, today there is a term called global warming and climate change, which is widely talked all over the world. And due to climate change, of course, we face different challenges, not only in the environment aspect, but also in human health. So there is a rapid change in climate. There is a rapid change in weather pattern. Uh, uh, Very high rain, very high drought like this. This is of course as a consequence of global warming. The main reason for global warming, that's because of accumulation of carbon dioxide in the atmosphere. So every year the amount of carbon dioxide accumulated in the atmosphere increases. So over the last 100 years, you can see a very high rise in the temperature, average temperature. So people are working on to reduce the CO2 emissions, which are emitted by different sources. What is the reason for the CO2 emissions? Of course, that is mainly due to the primary energy consumption, particularly coal and petroleum fuels. So the combustion of coal and petroleum fuels in different combustion devices emit a lot of CO2 emissions. Despite we have other emissions like unburnt hydrocarbon, carbon monoxide, sulfur dioxide, oxides of nitrogen, particulate matter, etc. The CO2 emission that is very much dangerous. As I told, that is the main reason for increase in global warming potential. So if you see this slide, the primary energy consumption by sector, in the left hand side of the slide you can see the primary energy consumption is accounts for 36% in electric power generation, followed by transportation sector which accounts for 30%, and then of course 20% is shared by industrial sector, and then remaining it goes to residential and commercial sector. Now you can see this right hand side of the slide, you can see the oil consumption in different sector, especially crude oil consumption, that is mainly utilized. Crude oil is mainly utilized in transportation sector, especially road transport. It accounts for 54%. Then, of course, industry, it consumes 16%. Then remaining it goes to residential. Then service sector, industrial energy consumption, and then other sectors. Next, please. So it is inevitable to avoid the consumption of this primary energy consumption or primary energy sources. Why? Because this crude oil, coal, everything is available by nature. So you have to continuously, of course, you have to use. Without using, not using this coal and petroleum fuels also, that will give problem. So in that sense, we can use this primary energy sources to some extent in future, but we have to just switch over to some other alternative fuels which can substitute. Of course, we cannot completely eradicate the use of primary energy sources, but we can replace, let's say, 20 to 30 percentage by the use of alternative energy sources. Especially you can see nowadays we use renewable energy sources like solar, wind, of course, hydro and ocean thermal energy sources. But apart from that, we can use biomass also. which is abundantly available in nature. Now, in transportation sector, we cannot control carbon dioxide completely because all automotive vehicles are mobile in nature. So CO2 is continuously CO2 emission is CO2 is continuously emitted because vehicles are moving. Therefore, we cannot completely control CO2 emission with any device. Stationary power plants which consume primary energy sources that can the primary, I mean, sorry, the power plants which use primary energy sources uh, that emit lot of CO2, but they are stationary sources. So in that sense, of course, carbon dioxide can be significantly controlled in those places, but not in automotive vehicles. Therefore, people, they think how to control CO2 emission and use alternative fuels in automotive vehicles. By the way, there are many options to the replace the petroleum fuels by the use of different alternative fuels which are derived from particularly biomass sources. Now, in biomass sources, we can get different fuels in the form of solid, liquid, and gas. Especially if you see this gaseous fuels, uh, there are two examples. One is, of course, what you call biogas, and the second one is hydrogen, which can be produced from biomass. Now, these gaseous fuels, they can be easily mixed with internal combustion engine if you use, or of course, on the other form, you can use this hydrogen in fuel cell fuel cells, or you can use it as it is in the IC engine, internal combustion engine. Despite this alternative fuels, especially the use of hydrogen in automotive vehicles, nowadays the entire world is, of course, talking about the electric vehicles. So here you can see the slide where you can see the examples of electric vehicles like electric two-wheeler, electric car, of course, electric bus, all come. But what are the main challenges with the electric vehicles? The first one is you must have infrastructure, adequate infrastructure. The second one is, of course, the battery. What do you use it for electric vehicle that supplies electricity or electrical energy? The battery is mainly lithium-ion battery. And the third one is, of course, uh, whatever the electrical energy what you get, that may not be sufficient to meet the demand. To meet the requirement of operating electric vehicles. For example, countries like India, we have a population of about 140 billion. And a vehicle, of course, everybody is using vehicle, different form of vehicles. And all these vehicles are converted into electric vehicles. Then the energy required to operate these vehicles will be enormous. So that much energy cannot be supplied by the currently available power plants. So in that case, the energy requirement is also very high. So people, they think on how to, of course, compensate that or overcome these issues. So by the way, of course, they propose, why not we use hybrid vehicles? Let's take like a vehicle which has both internal combustion engine and electric vehicle mode. So in that case, in city limits, we can use electric mode, and beyond the city limits, we can use internal combustion engine operated vehicles. Particularly if you see this internal combustion engine operated vehicles, of course, as I told you, there are many options to use. There are many options of fuels what we have, like, of course, biodiesel, then ethanol, in the form of liquid fuel. Then, as I told, of course, you have natural gas, LPG, hydrogen, all these things. Natural gas and the LPG, of course, they are obtained from petroleum industries. So, despite they are clean, they also emit, of course, carbon dioxide. But if you see this hydrogen, it's a very, very clean fuel. Hydrogen is a carbon-free fuel. So people want to use hydrogen as much as possible in automotive vehicle applications. Either directly they can use hydrogen as a fuel in internal combustion engines, or of course nowadays the the fuel hydrogen that can be used in a device called a fuel cell. That is also one way of converting fuel into electric energy. So fuel cells are also upcoming, especially uh, the history is way back to 100 years, but fuel cell fuel cells are also coming in the form of hybrid vehicles, in the hybrid vehicles. Therefore, we can combine ICE engine with electric vehicle, or ICE engine with a fuel cell, or fuel cell with electric vehicle. Like this, combinations are proposed nowadays in automotive vehicle applications. But the problem with the moving towards higher utilization is that the amount of hydrogen which is available, which is produced, that may not be able to meet the requirement of the uh, meet the requirement of fuel what we use in automotive applications. Therefore, all people, research community in the world, they are trying to, of course, explore the possibility of producing hydrogen in different ways. So, in that sense, today's lecture, what I will give, that is on this hydrogen production technologies. Next, please. So here, of course, I gave some examples like fuel cell, of course, fuel cell electric vehicle, hydrogen fuel cell vehicles. All this have already come in developed countries, but countries like India, we are having a lot of difficulties in producing hydrogen, which can be, used in fuel cells as well as internal combustion engines. Therefore, it is very high time, especially for country like India, to produce hydrogen in different ways. Country, of course, India, it is an agrarian country, which, of course, which is able to produce large amount of biomass. So people are interested in producing hydrogen, especially from biomass. So that I will elaborate, I'll talk in detail in this presentation. Now, uh, I'll go one by one. What are the methods available? How we can produce this hydrogen? Next, please. Of course, this uh, actually we are thinking about using electric vehicles everywhere, but of course, recently this BMW, it says goodbye to electric vehicle. It says that we will bring out, hydrogen engines which can meet out the demand of clean vehicles. As I told, electric vehicles, of course, it has different issues or challenges that cannot be met out immediately. So we can, of course, use electric vehicles to certain extent, especially India like a country where huge population is there. We cannot completely shift over from conventional ICE engine to electric vehicles. It will take a lot of time. So in that sense, of course, uh, of course, this BMW and other companies now in India, they want to parallelly, of course, bring out hydrogen engines, which can be, of course, used in hybrid mode with electric mode. Next, please. So this I told, of course, we can have combinations of internal combustion engine, then electric vehicle, or internal combustion engine, uh, fuel cell vehicle, and electric mode, fuel cell and electric mode. This kind of combinations have been proposed many years ago, but now it's slowly in transformation. It will be realized soon. Uh, Already, this kind of vehicles are available in countries like USA, Canada, Germany, UK, and all. But we will take a lot of time for this to realize. Next, please. So, hydrogen. Why we have to focus on hydrogen? As I told, we have different options of using alternative fuels like biodiesel, then of course ethanol, then biogas, LPG, natural gas, then of course hydrogen. All these things are there. Among all these fuels, of course, hydrogen is focused because, as I told, it's a carbon-free fuel. There is no carbon in it. Hydrogen, of course, it was earlier called as water creator. That was proposed by a Swedish scientist called Cavendish. Actually, hydrogen can react very well with oxygen, and of course, it will form water, as you know. And hydrogen, of course, if you see this, if you take water, it has two molecules of hydrogen and one molecule of oxygen. So the simplest way of course, getting hydrogen is by splitting water into hydrogen and oxygen. Hydrogen, of course, it's a colorless, odorless, and non-poisonous gas, but it's lighter than air and helium. It when you burn this hydrogen, it will show like a pale blue color, but almost it's invisible, so you cannot detect the flame what you get when you burn hydrogen. What are the merits of this hydrogen? Of course, it has a very high grammatic energy density. The calorific value or heating value is very, very high. It's about 1,20,000 kilojoules per kg, and it is available everywhere. Of course, water, you can take it. It is one of the most abundant element in the form of chemical compounds, and you will get zero pollutants like unburnt hydrocarbon, carbon monoxide, carbon dioxide, sulfur dioxide. Nothing will be there. But nitric oxides of nitrogen will be found, but that can be controlled, or that can be regulated. It Therefore we can call it as it's a very eco-friendly or environmental friendly fuel, and we can produce hydrogen in from different sources. But on the other hand, you can see there are three drawbacks. One is it has low volumetric energy density. That means you need a very big storage tank to accommodate this fuel in automotive vehicles. People are working on to, uh, store this hydrogen in the form of solid. That means we call it as metal hydride. There is a continuous research going on this aspect also, and it is highly inflammable. And because why? Because the flame velocity of hydrogen is very high, so it can quickly catch fire, and it's highly inflammable. But it is difficult to store at normal atmospheric condition. So if you want to store in the form of gas and liquid. Next, please. So if you see, earlier hydrogen was produced only by electrolysis. By splitting water by electrolysis, we'll get hydrogen and oxygen. So now, after the realization of alternative fuels and the need of hydrogen, there are many sources for producing hydrogen been found out. Therefore, based on that, in industry, different color codes are given for hydrogen, which are produced from different sources. Like we call it as green hydrogen, pink hydrogen, yellow hydrogen, turquoise hydrogen, brown, blue, white, like this. So although we just give this color codes, these color codes slightly vary depending on the country and time. Next, please. So here the hydrogen color codes, hydrogen production color codes are given. As I told, green, purple, yellow, blue, turquoise, gray, brown, like that. So each and every method by which hydrogen is produced is given in the second column. Of course, the third one is the feedstock or raw material, what we use to produce hydrogen, and of course, greenhouse gas footprint is also given. Now, if you see this electrolysis, as I told, that is one of the simplest ways to produce hydrogen. That means you split water so that you will get a hydrogen and oxygen. For splitting water, you need energy, electrical energy, right? So that can be obtained from different sources like wind, solar, hydrogen, geothermal, or tidal. Whatever renewable energy source you can adopt. If you adopt it to produce, if you adopt it to, you know, uh, break water through electrolysis, then the hydrogen what you get, that's called green hydrogen. The carbon, the greenhouse gas footprint is very, very minimal because we are using renewable energy sources in this method. Of course, if we use nuclear energy to, nuclear energy for electrolysis process, then we call it as purple or pink hydrogen. There also you get a minimal carbon footprint or greenhouse gas footprint. Then if you use mixed origin grid energy, means combined sources of energy, then the energy, the hydrogen what you get, that is called yellow, and the carbon footprint is medium, greenhouse gas footprint is minimum. Then we have, uh, of course, suppose we use natural gas or coal to produce hydrogen by the way of natural gas reforming and integrating carbon capture, utilization, and storage, or if you adopt gasification and carbon capture utilization, then we call it as blue hydrogen. Here also we get a greenhouse gas footprint is low. Then of course, natural gas, using natural gas, if you get hydrogen, then it's called turquoise. But here we get a solid carbon as a byproduct. Of course, the method what you use, that is called pyrolysis. From pyrolysis, we can get a hydrogen by separating the methane and other compounds. In that case, we can call it as turquoise hydrogen. Then, if we use a natural gas reforming process to produce hydrogen, then it's called gray. Then, one more technique is that gasification. Suppose I use brown coal, lignite, normally lignite. If I use it as a fuel or raw material, not fuel, raw material in gasification process, then it is called brown hydrogen. Finally, of course, you have black coal. Black coal also, of course, you can subject it to gasification process and get a hydrogen. Uh, then it is called black hydrogen. So these are the production methods what we have to produce hydrogen from different sources. Next, please. Now, hydrogen is used in many industrial applications, not only as fuel, it is used in different industrial applications. Here, of course, the left-hand side of the slide it shows the different raw materials or sources by which we produce hydrogen is depicted in this figure. Like as I told, we can use coal, we can use natural gas, we can use oil, or of course we can use electrolysis. Electrolysis is a process here. For that, we need electrical energy that you can obtain from different renewable energy sources. So here, if you see this coal, natural gas, and oil that are treated as fuel or feedstock from which we can get hydrogen. Now here, if you see, the most of the hydrogen is produced from, of course, natural gas and coal. Then, of course, electrolysis and oil. Here you can see the hydrogen utilization in industrial application. You can see in the right hand side of the figure. It is used for ammonia production. It is also used for methanol production and refining process and other uses. So hydrogen, of course, it's used in ammonia production, let's say about 28 megatons, and then followed by other uses or other applications. Next, please. So here you can see the need of hydrogen in industrial sector is continuously rising. That means from 1975 to 2018, you can see for different applications, hydrogen what is used, that is shown in this figure in million ton of hydrogen. So as of 2018, you can see 70 million ton of hydrogen that is used so far, right? So apart from this applications, nowadays we want to use this hydrogen for automotive applications as well. So the demand for hydrogen production is always increasing. Next. Now, of course, this slide shows the hydrogen production from different methods using different sources in each and every country in the world. That is shown. Now, here if you see, as I told, we can use coal, we can use biomass, you can use renewable energy sources like solar, wind and all to produce electricity first, then you can produce hydrogen like this. So different countries, they use different sources that that are highlighted in different colors here, green, blue, light blue, like that you can see. Next, please. So demand centers, you can see European Union, of course, it produces, as of now, it produces hydrogen on par with US. Regions like China and the US are both demand centers and have favorable renewable energy sources. So they produce hydrogen globally more than European Union and other countries. Next. Now, how we can produce hydrogen, that is very, very important. As I told, electrolysis is a very simple process because you take water, supply electricity, break water into hydrogen and oxygen. That's all. But other than this, we can use different sources uh, like biomass, coal, natural gas, everything, biogas also. So in that sense, we classify hydrogen production by using two different sources. One is fossil fuel and the second one is renewable energy sources. So if you see this fossil fuels, we have two methods. One is hydrogen reforming and the second one is hydrocarbon pyrolysis. So here hydrogen reforming, under a hydrogen reforming we have three methods. One is called steam reforming, then partial oxidation, and the third one is autothermal reforming. On the other hand, if you see this renewable energy sources, as I told, you can use solar, wind, biomass, everything. So in that case, we can classify under those sources into two. One is biomass process, second one is water splitting. Water splitting I told already. So in water splitting, you have three methods: electrolysis, thermolysis, photolysis. Electrolysis is the simplest one. By supplying electricity, you will get hydrogen and oxygen from water. Thermolysis and photolysis, where you will apply heat energy or solar energy for splitting water. Then, of course, when you use biomass as a source, Then we have two classifications. One is you can adopt two methods. One is hydrogen reforming, and the second one is hydrocarbon pyrolysis. So hydrogen reforming, of course, it has three methods. One is biophotolysis, second one is dark fermentation, third one is photofermentation. On the other hand, hydrocarbon pyrolysis, where you have three methods. One is pyrolysis, gasification, second one is gasification, and third one is liquefaction. Next, please. Now, of course, worldwide, the emerging research is going on hydrogen production using solar energy, and then of course wind and other energy comes. Now, solar energy can be used to produce hydrogen by by adopting different pathways or routes. From solar energy, you can get heat using concentrated solar power plant, and then that can be used to produce hydrogen via thermolysis. Then, of course, you can also produce mechanical power from solar power plant. Heat will be converted into mechanical, and then you can use mechanical energy to produce electricity, and then that electricity can be used to break up water through electrolysis process. Of course, other energy sources like wind, geothermal, ocean, hydro, all these sources can be used to produce mechanical energy first, or mechanical power. Then that mechanical power will be converted into electricity with the help of turbine. Then, of course, then that electricity can be fed to produce hydrogen via electrolysis process. Then we have biomass. In biomass, we have two different routes. One is by adopting biochemical, by using biochemical conversion method. Second one is thermochemical conversion. Hydrogen can be produced. That I'll come to that. What are biochemical conversion processes? What are thermochemical conversion processes? The next one, you have photobiological process. Photobiological process means what? By using sun, solar energy, you can biologically convert some substances into hydrogen. That is called photobiological process. So via photolysis, you will get hydrogen. Then photoelectrochemical conversion. That is the another route by which you will get hydrogen via photolysis. Next, please. So, if you see this, hydrogen, as of now, commercially hydrogen is produced by involving four methods. One is steam reforming, second one is water shift gas reaction, then partial oxidation, then autothermal reforming. Of course, the main feedstock what we use to get hydrogen through this conventional processes like steam reforming, water shift gas reaction, partial oxidation, and autothermal reforming, or of course coal, natural gas, then LPG, naphtha also. So this can be converted. Normally they are called carbon feedstocks. They can be converted into hydrogen by adopting any one of these processes like steam reforming, water shift gas reaction, partial oxidation, and autothermal reforming. So if you take the steam reforming, normally we call it as SMR. In chemical engineering, we call it as, or chemical industry, we call it as SMR process. So as I told, it can use variety of carbon feedstocks. Of course, biomass also, that can be first converted into biogas, and then it can be converted into hydrogen via the steam reforming. That I'll come to that later. Now, steam reforming, it is the simplest form of using methane as a feedstock. That's why I told biomass can be first converted into biogas, and then we can convert into hydrogen via this method. Natural gas here, is heated between 700 to 1100 degrees Celsius in the presence of steam and a nickel catalyst. So nickel is used as a catalyst to speed up the reaction. And of course, when natural gas is heated at this high temperature, it will break away. So as a result, this natural gas which contains methane, that will be converted into carbon monoxide and hydrogen. Then you can separate this hydrogen. Next, please. So here, of course, this CO gas that is separated from hydrogen. Now, actually, here we have elements like CO, CO2 and other greenhouse gases that will be separated. Again, what kind of feedstock we use, based on that you will get very high quality or low quality of hydrogen. 1 ton of hydrogen produced will also produce 9 to 12 tons of carbon dioxide. But people, especially now in developed countries like US and all, they are capturing this carbon dioxide and utilizing in different means from these refineries or hydrogen production units from natural gas. So here, as I told, when you subject naphtha at a high temperature, when you heat, sorry, not naphtha, natural gas at a high temperature, you will get this reaction like CH4 plus H2O, that will give carbon monoxide and 1 mole of carbon monoxide and 3 moles of hydrogen, like that. Now, of course, we have a second stage or second step. In that, additional hydrogen is produced through the low temperature exothermic water gas shift reaction, which is carried out at temperature range of 300 to 400 degrees Celsius. Again, depends on the feedstock. Here, of course, what we do, oxygen is stripped out from the additional water that is supplied, normally steam that is supplied to oxidize CO into CO2. So that is called the water gas shift reaction. Next one. Now, this water gas shift reaction I told, it forms CO2 and H2 using water and CO at elevated temperature. So here, of course, you can use catalyst if you wish. Again, depending on the feedstock, what kind of feedstock we use. Then, of course, partial oxidation. Here, what we do, normally it's a basic gasification reaction, which helps to break down hydrogenated carbon feedstock. It may be coal or petroleum coke, whatever it may be. With the help of heat, we can crack down or break it to get CO and H2. So that's called a partial oxidation. So here, of course, once you get this CO and H2, you can adopt different methods to separate H2 from that. So normally, this composition, gas composition, normally CO and H2, that's called syngas. So syngas, of course, that will be of course separated. That means H2 and CO, that will be separated. So we can adopt like membrane technology is there to separate the hydrogen, or we can also use liquid absorption of CO2 or other gas impurities, so that we can get more amount of hydrogen from this partial oxidation. Next, please. Then, of course, autothermal reforming. Here, of course, it is the term normally called to combine the word or combine the term like steam reforming and partial oxidation in a chemical reaction. So here it occurs when there is no physical wall separating the steam reforming and catalytic partial oxidation reactions. So what you do normally, here also we use catalyst that controls the entire reaction, so that we'll get hydrogen at the end of the process. Here, this autothermal reforming, we can operate at a low temperature compared to this partial oxidation. So when you do like that, of course, at very low temperature also you can produce higher amount of hydrogen. Next. Next, please. So now, actually, biomass can be used to produce hydrogen by adopting two different routes. One is called biochemical conversion and the second one is thermochemical conversion. Normally in biochemical conversion, what we do, we of course we use what you call yeast or bacteria like that, microorganisms, to fractionate the feedstock to get either biogas, or we can adopt what do you call biochemical conversion. We have two methods. One is, I'm sorry, we call two methods called uh, digestion, anaerobic digestion, and the second one is fermentation. Through these two routes, we can produce biogas in anaerobic digestion and ethanol in fermentation process. So here, with the help of microorganisms, with or without the pressure, application of pressure, we can get biogas and fermentation, biogas and ethanol. This can be further converted into hydrogen. That I'll come to that later. In thermochemical conversion, we have, as I told earlier, we have mainly three methods: liquefaction, that is one; second one is pyrolysis, and the third one is gasification. So in thermochemical reaction or thermochemical conversion process, the feedstock is converted into hydrogen with either adopting pyrolysis or gasification or liquefaction. So here we need to apply heat, uh, slightly heat with or without pressure. Then what is the difference between pyrolysis and gasification? In pyrolysis, of course, there is no presence of oxygen or very less amount of oxygen present in the process. Whereas in gasification, of course, oxygen is allowed. Now, under three routes, of course, pyrolysis, gasification, and liquefaction, we can get hydrogen. Now, I'll talk about this biomass pyrolysis. In biomass pyrolysis, what we do, we get different feedstocks. Any kind of feedstock you can use, particularly it may be a solid one. That is preferable. Liquid also, of course, people are working on to fractionate liquid, liquid feedstock to hydrogen. But it is most of the research works they carry out by taking solid feedstock. Now here, of course, in pyrolysis, what we get a mixture of different substances like hydrogen, methane, CO, CO2, and other gases. What kind of feedstock we take, based on that we'll get the gaseous product. That will be separated so that you will get hydrogen. We have two more products like liquid and solid. Liquid is carrying, of course, the tar and oil. Now people are, taking oil which is obtained from pyrolysis process and they convert into hydrogen. Solid product, what you normally get in a pyrolysis process, that's called char and inorganic compound. So you will get a very less amount of hydrogen from that, but people are working in this as well. Next, please. Next. So this slide you can show, of course. Actually, in pyrolysis, what we do, any biomass substance that is fed in a pyrolysis reactor, and that pyrolysis reactor that is completely free from oxygen or little presence of oxygen may be there. That pyrolysis reactor is heated up. When it is heated up, the biomass substances which is fed there in the reactor that's heated up, volatile matter from biomass that will rise, that volatile matter that will be condensed in a condenser, so that you will get the three different products I told, like gaseous product, liquid product, and solid product. Normally, if you use biomass substance, then we'll call as bio oil, which is available in the form of liquid. Then gas, what you get, which is normally not condensed, that is called pyrogas. That of course that composes carbon monoxide, carbon dioxide, and hydrogen. That the hydrogen can be separated. Now this bio oil, people are working on to, of course, convert into hydrogen, and finally you will get a solid substance in the reactor. When you use biomass as a feedstock, the solid substance what you get it in the reactor, that's called biochar. If you use any industrial waste, any other form, and the solid substance what you get, that's called carbon black. So this also can be, of course, refined to get refined, and then further process to get hydrogen. People are working on different directions. Now there are different parameters that affect the feedstock what you use in the reactor, pyrolysis reactor. So if we take biomass, so the important parameters that affect the hydrogen yield what you get it in the pyrolysis process later in later stages, that depends on the feedstock what you first give it as input. So important parameters include particle size, moisture, composition of feedstock, like that. In the reactor, different parameters they influence, like feed rate, heating rate, temperature, gas flow rate, retention time of the pyrolysis, or residual time, what you say. So these factors influence the quality of these three products what you get, like bio oil, biochar, and gas what you get, which is not condensed. So these three products that will vary according to the type of feedstock what you use and the influential parameters. Now this bio oil, of course, that is mainly focused now to get a hydrogen. So of course, the quality of bio oil, it depends on how much water is present in that, water content, viscosity, and the bio oil composition and the nature. Next. So here the illustration of pyrolysis is given. Normally biomass, you can take any biomass, first dry it, then grind it, and then feed it to a reactor, and you can heat up. Of course, as I told, the pyrolysis can be carried out either in the presence of little presence of oxygen or completely free from oxygen. When you want a completely free from oxygen, then the reactor must be evacuated before you feed that. So people they purge nitrogen, which is an inert gas. They purge nitrogen into the reactor, completely evacuate oxygen, and then they use the reactor for the pyrolysis process. So the volatiles which are raised from the reactor, that will be first sent to a cyclone separator, where high density particles that will be removed. Then the gas will be given to a condenser. So when the gas is condensed, that's volatile matter is condensed, you will get the bio oil. Then of course you some of the volatile matter may not be condensed. That will be taken as a gas, non-condensed gas. That will be given for drying the biomass feedstock. Then of course you will also get, as I told, you get a char that can be separated from the cyclone separator as well as reactor, and that can be further processed to get hydrogen in a minimal portion. That I don't focus. Only people now working on is that to get hydrogen from bio oil and of course gas. Next, next please. So here of course different biomass feedstocks were used to get hydrogen using biomass pyrolysis, like wheat straw, pine wood, of course wood, like that. You can see in the left hand side column of this table, many researchers used different catalysts as well. Of course, nickel, magnesium oxide, zinc, like that. And of course, what kind of reactor type they used, that's shown in third column. Reaction temperature. As I told, reaction temperature is also an influential parameter to get the quantity and quality of bio oil what you get. Then, of course, when it is processed, you will get different quality of hydrogen. So how much hydrogen yield you will get, that is also shown in the last column. Next, please. Then liquefaction, of course, liquefaction can be given in two forms. One is direct liquefaction and the second one is hydrothermal liquefaction. Of course, you liquefy any substance, that's called normally liquefaction. It's a small process. Hydrothermal liquefaction, that's also called hydrospyrolysis, where the biomass is converted into liquid fuels in the presence of water by maintaining a temperature between 226 degrees Celsius to 362 degrees Celsius with the application of pressure ranging from 5 to 20 megapascal. So you have to have a catalyst in this process as well. That means hydrospyrolysis. So you'll get a liquid product that will be further processed to get hydrogen. So here people, they use aquatic biomass, garbage, organic sludge, like that. They investigated to get hydrogen from this kind of this kind of feedstock via liquefaction process. Next, please. Then, of course, here this table shows different feedstocks which are considered to produce hydrogen via liquefaction of biomass is given. That I just pass it. Next, please. Then biomass gasification. Of course, under thermochemical conversion process, we use gasification also. So here, of course, in gasification, what we do, we feed a feedstock in a gasifier, and oxygen is supplied very little quantity, and then the gasification process is carried away so that you will get a product called syngas. That syngas normally it composes carbon monoxide and hydrogen. So this syngas, of course, that will be separated by adopting different process. So the gasification, normally in the gasification process, will get carbon monoxide and hydrogen as a primary product. Apart from that, we'll get some minor gases also. Minor gases, as well as we get tar. That I'll come to that in the next slide. So what kind of biomass you use, based on that you'll get the syngas quality and the tar quality. So here this slide, it shows how the gasification is carried away. Biomass is fed, first pre-processed, and then it is given to a given to your gasification process. It's fed into a gasifier. So you have to, of course, you have to supply gasification agent, normally oxygen or air. Then you will get the syngas that will be cleaned and upgraded, then cooled. Then we'll get the separation of gases, hydrogen, CO, CO2, CH4 and all, they'll be separated. This is a basic idea what you get in gasification process. Next slide will tell or will give more information. Next, please. So here, of course, air is used, or you can use oxygen, but normally air is cheaply available, so we can directly feed that. Biomass is fed into the biomass gasifier. So here at the bottom you will get tar or ash, and of course you'll get gas also. This gas, it composes of carbon monoxide and the hydrogen. So here we have three zones that I will show in the next slide. Normally we have oxidation, pyrolysis and combustion zone. Next slide, please. Next, you can skip this. Next. So here, this one, of course, we have three zones: pyrolysis zone, pyrolysis zone, reduction zone, and combustion zone. I told oxidation by mistake. So we have pyrolysis zone, reduction zone, and combustion zone. So based on the nature of the gasifier what we use, the zones may just slightly change. So here you can see, normally we use two different gasifiers. One is called updraft gasifier and the second one is called downdraft gasifier. Of course, gasifiers, they have different types that I don't get into that. But simplest way is using updraft gasifier and downdraft gasifier. So here, the way by which you feed the feedstock and air, we call it as updraft gasifier and downdraft gasifier. So here if you see this updraft gasifier, air is supplied at the bottom of the gasifier. Air travels from the bottom to the top. So here first combustion zone will be there, followed by reduction zone and then pyrolysis zone. So you have to feed the feedstock at the top of the gasifier. Here you get the gas. Normally the syngas is obtained at the top of the gasifier. On the right hand side, you can see the downdraft gasifier where the gas is obtained at the bottom, collected at the bottom, and air is supplied at the side of the gasifier. Right? So here also we supply the feedstock at the top of the gasifier. Next, please. So ash is a big problem in the gasifier. Continuous ash mole is a problem. So here, no, previous slide, please. So the quality of syngas is very, very important. Syngas, it contains carbon monoxide and what you call carbon monoxide and hydrogen. So there are different issues associated with the gas cleaning and the yield what you get for hydrogen. Normally, the moisture content present in the gas that's a big problem, and the tar formation, that is the second problem. Continuously, you have to remove this tar. Normally, you can use dolomite to reduce this tar, and of course, you can increase hydrogen production or a hydrogen yield. Moisture content in syngas that cannot be completely removed, because what kind of biomass we use, based on that you will get slightly moisture that will be present in the gas, that you have to remove first before of course cleaning. Here of course once you get the syngas, we can use catalytic steam gasification. Catalytic steam reforming. Catalytic steam reforming, of course, it helps to get intermediate volatiles that formed in the gasification zone. Right? So you can use catalyst to get more amount of hydrogen from the gasification process. Of course, whatever you get the syngas, that has to be converted or that has to be further processed to get a hydrogen. You can adopt either water gas shift reaction or steam reforming reaction. Next. So here we can use two different catalysts to enhance hydrogen production in the gasification. The primary catalysts, normally they are added directly to the raw biomass or raw feedstock before gasification process, so that you can get a more amount of gas. And the main purpose of using this catalyst is to reduce the tar content, on the other hand. But the problem is you have to continuously remove, as long as you operate the gasifier, you have to continuously remove this tar. So here this primary catalyst, they help to increase the gasification rate, reaction rate, and increase the hydrogen production also, that I told. Then the second one, we can also use secondary catalyst that are placed in reactors, inside the reactor itself. So once the gasification process starts, they'll help to increase the hydrogen or syngas production rate. So by this way, we can use catalyst to enhance the yield of hydrogen which is produced. Next. Of course, nowadays people they use supercritical biomass gasification also, which is slightly advanced version of this gasification process. Here, when people they adopt supercritical biomass gasification, they used a different feedstock like glucose, olive mill wastewater, switchgrass, biocrude, bark, sewage sludge, like that. So from that they got hydrogen at the different yields. So that is shown here. What kind of reactor they use and what kind of catalyst they use, that is shown in this table that you can see. Next, please. Now, next. So this is solar gasification. Of course, this is one more advanced research. What you get, that's called solar gasification. So with the help of solar collector, we can apply heat. Actually, in gasification, you have to apply, that gasification. In a gasification, what we do with the application of heat and pressure, or without pressure, you can get the syngas. So for application of heat, here they use solar collectors. So with the help of solar collector, you get a heat. That heat is fed to the gasifier, or normally we call it a solar reactor. So then we get, the syngas that is obtained at the bottom, as shown here. So wet biomass that is fed to the gasifier. So with the help of solar reactor, you get heat that is given to gasifier, and then normal gasification process it occurs. Then you get the compost gases like hydrogen, CO, CO2, CH4, all these things you'll get. Then you have to separate it. Next. So here, of course, when you use solar biomass gasification, what kind of yields you get, hydrogen yields you get, that is shown at the last column. The feedstock, different feedstocks used by different researchers are given in the left-hand side, first column. So here you can see what kind of light source or catalyst is used in solar biomass gasification, like solar power. Then you can see at the bottom solar heat by high flux simulator, like that they are using. From there they get the heat, and then they adopt the gasification process. Next, please. And of course, non-thermal or biological process. Non-thermal means what? We don't supply heat or we don't use heat, but we adopt biological process. As I told, of course, you can use biogas. From biogas, you can get methane. Then methane can be converted into hydrogen. That is one route. In addition to that, we use biophotolysis also. So here we have two biophotolysis process. One is direct biophotolysis and the second one is indirect. So in the direct biophotolysis, microalgae photosynthesis system that converts solar energy into chemical energy that results in hydrogen production from biomass. So that is one route. Now it is recently adopted, and it is upcoming research in hydrogen production. So here generally people they use it freshwater algae as a feedstock. They are used in fermentation, and algae that are utilized in seawater. These two are used for producing hydrogen. So here, with the help of this process, we can get a more amount of yield from biomass substance, especially algae. And here there is no need for substrate. Like in biogas, what we do, digestion process is carried out, anaerobic digestion process. So here we don't do such kind of process. Straight away we get hydrogen from biomass. So here we have two steps in this biological hydrogen production. One is growth of cell that takes place, and the second one is production of hydrogen. Next. So here an illustration is shown. Photons from sunlight that is obtained, that is given to uh, a reactor, photopyrolysis reactor, and that is subjected, the feedstock is subjected to this biophotolysis with the application of sunlight. Then you get hydrogen. So here there is a process called hydrogenase. From then you will get hydrogen. Next. So here you are using two systems. One is photo system 1 and the second one is photo system 2. So photo system 1, that is used for carbon dioxide reduction, while photo system 2, that is used to produce hydrogen by splitting water. So here, of course, with the help of solar energy, we get next indirect biophotolysis. So here, actually, there is a bacteria used, cyanobacteria, that converts biomass into hydrogen by using two stages, as like previous one, namely photosynthesis and then fermentation. So normally this photosynthesis and fermentation, that is carried out with the help of sunlight, of course, without sunlight and in the presence of hydrogenase. So here, of course, we get more amount of hydrogen because what you get, uh, what kind of feedstock you use, that's very, very effective in producing hydrogen. That's why the overall conversion, uh, in spite of the methods you use in the previous one, we get a maximum 16.3 conversion efficiency from the feedstock to hydrogen. Next. So here you can see there are two stages. This, of course, here we have photo system 1, then you have cellular material. In between that, reaction takes place and you get hydrogen. Next, please. This and all, it's purely, biological oriented. This also you can skip. Photo fermentation, of course. Photo fermentation, in fermentation, what we do? For example, we produce, in normal fermentation process, ethanol is produced using yeast. But here in photo fermentation, photosynthetic bacteria that utilizes the nitrogenous matter that converts into hydrogen. Nitrogen matter, the photosynthetic bacteria that utilizes the nitrogenous matter to convert biomass into hydrogen. And that happens in presence of sunlight. That is very, very important. Next. So this one through photo fermentation. So here, of course, we have three stages: biomass preparation, preparation and processing. Then we have photo fermentation, then separation. So here, of course, biomass is fed for processing. Processing means what? First, you have to classify it, mesh it. Then, of course, we boil and then we subject it to photo fermentation. So here we allow yeast in the reactor for photo fermentation reactor, and substrate is added, and the fermentation takes place. Then we get a mixture from where you will get a hydrogen and CO2. So here the conversion efficiency about 3 to 10% in the photo fermentation process. And the size of the reactor requires big. So that is one of the, what they call, a hurdle for carrying out the research. Next one. One more thing is there, dark fermentation. So this, of course, This I skip because of time. No, this one. So here, of course, next, please. This also you can skip. These are all results, of course, results of dark fermentation. Previous slide. Next, next. I'm sorry. Challenges are there, no? Opportunities and challenges. Of course. Uh, what are the opportunities and challenges in hydrogen production? Of course, as I told in the earlier slide, the first slide, there's a big gap between supply and demand. How much hydrogen is produced as of now, that is not sufficient to meet the requirement in automotive application. Therefore, it is necessary to produce large amount of hydrogen. In current practice, coal, natural gas, and water, they are used as main feedstock. Of course, coal and natural gas. And of course, water. If you have abundant water, then water can be converted into hydrogen through electrolysis process. Despite that, if water is not water is not present, then we cannot carry out electrolysis process. But now people do research using wastewater available in industry and municipalities. So wastewater can be converted into hydrogen, but first we have to of course convert wastewater into water and then water into hydrogen by electrolysis process. People, of course, they are doing this research how to convert wastewater into hydrogen. Then, of course, we use renewable energy sources like solar, wind, hydro, and geothermal, but they are not explored as much as possible in hydrogen production. And of course, the main scope what you have currently is that we can produce hydrogen from biomass as much as possible, so that we can have startup units which can produce hydrogen and we can supply. And of course, when you use renewable energy sources, that hydrogen production unit must be installed near to the source what you have, renewable energy source. It may be solar or wind or geothermal, whatever it may be. So you need to install. We need to combine these two sources, whether solar and wind or solar and hydro, like that, and then you can produce hydrogen as much as possible. At large facilities, and then of course you can large facilities, you can produce hydrogen as much as possible at one point or single point. uh, you can also have a distributed production units, that is possible. Next. So as of now, the production cost is very, very high. If you reduce the cost of hydrogen production, then of course uh, hydrogen can be used in a large quantity in automotive application. So here one more important challenge is that the catalyst, microorganisms, are all what we use in different processes. Their cost also involved in hydrogen production. They have to be reduced. Otherwise, the total cost of hydrogen production will be still more. So people are working on catalyst, biocatalyst, chemical catalyst, biocatalyst, of course, enzymes, like that, to produce hydrogen. So still there is a lot of, there is a long way to uh, produce hydrogen from different sources. Anyhow, uh, I hope India will produce the at least a significant quantity of hydrogen in forthcoming years. So due to time availability, I have to skip some of the slides. So I'm sorry to speed up my this presentation.
No,
Next,
it's fine,
please.
sir. It's okay, sir.
So here I want to conclude. I want to summarize. So here actually I told different methods like steam reforming, partial oxidation, autothermal reforming, of course biomass gasification, aqueous phase reforming, electrolysis, photolysis. Different technologies have been explored so far by many researchers. Different feedstocks. If you see this steam reforming, conventional process like steam reforming, partial oxidation, autothermal, they use coal, natural gas, naphtha, like that. They are all hydrocarbon feedstock. Biomass gasification uses biomass. Pyrolysis uses biomass. Of course, electrolysis uses water, and photolysis uses water and sunlight. Thermochemical water splitting uses water and heat, like that. So their efficiencies are given in the third column. If you see this, look at this efficiency values. As of now, if you see the conventional process like steam reforming, partial oxidation, autothermal reaction, you can get a conversion efficiency up to 75%, 85 percentage. That means it varies from 60 to 85 percentage depending on the parameters influenced. Whereas if you see biomass gasification, electrolysis, all will account from 30 to 70 percentage. So their maturity level are also shown in the last column. How far they are matured, technologically matured, whether you can go for commercialization or not. So there it is given. Steam, as I told in the earlier slides, the conventional methods like steam reforming, partial oxidation, autothermal reforming are currently in practice. So they are already commercially available. But if you see this plasma reforming, it has to go a long way. Then biomass gasification that's available commercially, and the last one, photolysis, direct photolysis, indirect photolysis, thermochemical water splitting, all will require long-term research. So after that, you can achieve the benefits. So with this summary, I wish to stop this presentation. If you have any query, you can ask.